The Power Estimator is a spreadsheet that allows you to enter design data into boxes. That is, activity rates, number of resources, clock frequency, etc., and quickly generates a power estimate. This spreadsheet segments each design by resource type, so for each resource shown here, we'll have its own page in the spreadsheet. This is a good time to remind you that the power consumption of each resource is significantly different. In fact, ideally, you will target the dedicated hardware resources as much as possible rather than just use the CLB logic resources. This is because the dedicated hardware is optimized for minimal power consumption and high speed. So be sure you're getting the correct hardware resources inferred by your synthesis tool, since this will choose which resource to map to based on your HDL coding style, unless you instantiate a particular resource. To help you with what we have for coding, we've produced several free recorded e-learning modules available at support.xilinx.com, which explain how to optimize your HDL code. Writing good HDL is of course important because it is used by synthesis tools to infer the most popular FPGA resources, that is of course LUTs and registers. Since there is very often more than one way to code for effectively the same functionality, it is important to understand the differences between two different or more ways to code a function. This is compounded by the fact that often a poorly coded piece of logic creates a timing critical path for a designer to resolve, and often designers will waste a great deal of time resynthesizing and repeating a place and route, hoping to meet a timing objective. Now this slide is trying to highlight some of the benefits of the dedicated hardware resources that exist in the newest FPGAs. The most useful of the dedicated hardware resources is the DSP slice and the block RAM resources. Besides using less power and saving primary FPGA resources, that is, LUTs and registers, using these dedicated resources makes it easier to estimate your timing. This is because the architecture delays of the dedicated resources are known before place and route is completed. Unlike data paths that may contain multiple LUTs and NITs in series, data paths that use the dedicated hardware resources do not require any programmable routing delays, except to route to and from those dedicated resources. Another reason to use the dedicated resources is that compared to soft implementation, that is a LUT and register implementation, the speed is significantly higher. So be sure to use as much of the dedicated hardware resources as your design needs, and if you think you may be running out of the primary FPGA resources, consider implementing more of your design in leftover dedicated hardware resources, like the DSP slice or block RAM. First of all, the Power Estimator is just an Excel spreadsheet that has your device's thermal information already built in. When you open the Power Estimator, you will see a summary sheet as you see here. This tool will use a default activity rate of 12.5% and will use standard operating conditions, but all of these values can be modified by the user. You simply enter new values in each white box and the new power estimates will automatically show up in the gray boxes. Note that at the bottom there are tabs for each FPGA resource type. So before you can see the total power consumption, you'll have to go to each resource page and enter the amount, frequency, and activity rate for each resource. Then the new power estimate information will be updated on the summary page. The summary page includes information you have chosen, including package, ambient air temperature, airflow, board selection, and power supply voltages. It also segments power by logic resource and provides an expected junction temperature. It will even break down power consumption by quiescent and dynamic power. This slide shows you how your clock, logic, and I/O resources can be customized. The clock tree power consumption is dependent on the distributed clock frequency, fan-out, and use of the global buffer. That is, specifically if the clock buffer enable is used. The logic power estimate requires clock frequency, number of logic resources by type, in this case that could be a LUT, shift register LUT, distributed RAM, and flip-flop, that is associated with each clock domain. This will also require you to estimate the average activity rate, shown here as a toggle rate. It also asks for the average fan-out for each resource. This allows high fan-out nets to be estimated as well. The I/O power requires the same kind of information, except it also needs your output loading and some details about how each IOB will be configured. That is, what I/O standard is used, whether the output enable is used, data rate, SerDes functionality, I/O delay, and of course slew rate. As you will see, I/O power consumption is a considerable factor in your overall system power consumption. This slide shows you how your block RAM, DSP slice, and your clock management resources, that is the MMCM resources, can be customized for the power estimator. The block RAM and DSP slice resources need a little more information that is specific to those resources than, say, the CLB resources needed. The clock manager, or MMCMs, need specific information about how each derived clock signal is going to be made. You may recall that each has the ability to derive up to 6 clocks and will be dependent on how each clock output was derived and its frequency. The Power Estimator spreadsheet also includes some graphing functionality that allows you to see how your FPGA's power is being consumed. In this case, our piddly little example design we're working with here is mainly consuming static power. As you can see from the upper left-hand corner graph, the bar chart for leakage is by far the largest. Well, that's because this design is very, very small, not even a fair test case, but unfortunately it was all I had. This chart is probably the most helpful because it easily allows you to determine which device resources are using the most power. This is helpful in case you decide you have a power problem. Then you can determine where your power is going and perhaps consider making some design changes to reduce the amount of those resources. Remember how I mentioned earlier about trying to target block RAM, DSP slices, or other dedicated hardware? So this porting to the dedicated hardware is a great design alternative. It also will allow you to direct your knowledge to the I/O pins. So if you're using a lot of power in your I/O pins, then maybe you can consider altering maybe the I/O standard you're using or the drive strength on those pins to reduce your power consumption. But we'll talk about other options you might have to reduce your design power consumption a little later. Further to the right, we see a chart for power versus core voltage behavior, and it's described. This will give you some idea as to whether increasing your core voltage, which in turn improves your system speed, can be tolerated thermally. On the bottom, the power variance for core voltage and temperature for your chosen device is shown. This allows you to see the impact of ambient temperature and core voltage on your device. And on the bottom right, the current versus your junction temperature is also shown. The XPower Analyzer is another power estimation utility. The difference is that it requires the design to be built, synthesized, and implemented. That means that this estimate is even more accurate than that produced by the Power Estimator spreadsheet. However, you will still need to supply the same information about the performance of the design, such as clock frequencies, activity rates, capacitive loading, power supply information, and ambient temperature. While this same information can be loaded manually, it also can be read in from a VCD file, which is a detailed design activity data resource from your simulation tool. A value change dump, or VCD file, is created by a simulation tool, such as Mentor Graphics Model Sim, for example. The VCD file contains information about signal or variable value changes. The VCD can be read by the Xilinx XPower Analyzer to provide accurate power estimation. Note that in order for the XPower Analyzer to match instance and net names from the VCD file to items in the NCD, that is your implement result, the VCD file must be from a post place and route simulation. The XPower Analyzer is located in the IC tools beneath the place and route. From here, you can start the utility or load the VCD files or run the XPower Analyzer from the command line. To load a VCD file, you right-click on the XPower Analyzer to open the process properties and browse to the simulation output file location.